Okay, here are the answers to the homework. Number 1 is A. Number 2 is D as in dog. 3 is D as in dog. Number 4 is A. Number 5 is A. Number 6 is B as in boy. 7 is A. 8 is D. 9 is A. 10 is B as in boy. 11 is D. 12 is C. 13 is A. 14 is D. 15 is C. 16 is C. And 17 is D. Hold on one second. Okay, what's your question, Miriam? 1 is A, 2 is D. Anything you want to ask about on these questions before we take a quiz? Yes. Yep. All right. In question number 1, we see this boy riding a bicycle, and he is, whoops, I just hit the wrong button. And you can see he's riding the bike to the right. Okay, so when we have an object like what you see there, the ball is also traveling to the right, right? Because he's holding it. So that means when he lets it go, the ball is not only moving to the right, but it's also going to fall. So we are asking you to describe the horizontal motion. That's our gravity-free path. In the gravity-free path, we travel with a constant velocity, in this case, to the right. So which one of these graphs shows us moving to the right with a constant speed? It's graph A. It is not graph D, which would be the other one you might think about, because this one shows us going left. That ball is not going to go to the left. It's going to go to the right with the bike for a period of time and then down. Okay? Anything else you would like to ask about? 1? Yep. Number 2, obviously A and B are out because we don't even know what kinetic energy or momentum is yet. So those are not good distractors for you because you don't even know what they are. So I want to know, it says if I have a 1 kilogram object being thrown horizontally and a 2 kilogram object being dropped from the same instant, from the same point above the ground, at any given instant, what do both objects have the same of? Now, remember we looked at that example with Mythbusters, the bullet being dropped and the one being fired horizontally. And I showed you an animation of something being dropped and something going sideways and down. And they always come down together. They always fall at the same rate, which means they're always going to have the same vertical height at every moment in time. They do not both have the same total velocity because the one that's going sideways has a sideways and a down component. The one that's dropped only has the down component. So the total velocity is not the same for both. Anything else you would like to ask about, Kiara? Yep. Number 7 says, what's the direction of the acceleration? The acceleration is always gravity. Which way does gravity always point? Down. A. Anything else? Yep.
If it has an initial velocity of 1 second, should it have an arc?
Should what have an arc?
Even if the object is falling, it should have it should go up.
It is right here. You see, after a period of time, it's going to come out and land right there. There's your parabola. The 20 meters per second is only its initial velocity, which is horizontal because it's being shot horizontally off the cliff. There is no vertical velocity to start. Khalees? Number 11. Okay, this one is about the information up here, which this is actually a question from the last unit, Unit 4, where we are projecting vertically upward from the surface of the earth, this ball, with an initial velocity of positive 49 meters per second. It's going to reach its maximum height in 5 seconds. I want to know which graph represents the relationship between the velocity and the time for that ball. As it goes up, it's going to slow down in the positive direction. Eventually, it's going to stop, have a velocity of 0, and then it's going to come down, speeding up in the downward direction. The only one that shows that is point D. This is showing it slowing down in the positive direction, stopping right there, and then speeding up in the negative direction. That's choice D. Anything else? Kiara? So question 15 asks us, which of these vectors represents the acceleration? The acceleration is gravity. Which arrow represents gravity? See, gravity is always down. Anything else? Okay, please take out your Chromebooks. Today's quiz is on your Chromebook. You should not need anything to do today's quiz. So you can close up your packet while you take the quiz. It's all conceptual based upon the notes from our last lesson. Good luck on the quiz for Unit 5A. Nothing. You get nothing except your Chromebook for today's quiz. Emma, do you have a pass? Okay. When you finish the quiz, you can put your Chromebook away. Shh, we shouldn't be talking. People are taking the quiz. I'll give you 1 more minute to wrap up the quiz. All right, ladies and gentlemen, please turn in your packet to page 15, where we left off the other day. You'll also need your reference table and calculator. We're going to work on completing the rest of the problems associated with horizontally fired projectiles. And at the end of our class period on Monday, we were working on question 4, where we found the time. Now, your assignment for tomorrow, before I keep working on those, is page 19 and 20 in this packet for tomorrow. Pages 19 and 20. You'll see on those 2 pages, there are 4 questions for you to complete on your own. Tomorrow's quiz is a show work quiz. Well, I will give you a horizontally fired projectile problem to solve, just like the ones that we are working on in class during period 3 on Monday and what we're finishing up today. Okay? So let's get back to page 15 where we left off. And on problem 4, what we did was we found the time and we wrote it in our chart. And ultimately, we were trying to find the initial velocity in the x direction, which means if I'm looking for something in the x direction, I would completely ignore what's in the y direction. So notice that in the x direction, I now have the a, the d, and the t, but I'm looking for the vi. What equation off the reference table can you use to solve that question if you have the a, the d, and the t, and you're looking for the VI? Who can tell me? What equation can we work with? Haley? That's right, the same one. But in the x direction, the a value is 0. So that part of the equation will drop out, leaving us with d is VI times t. So if I isolate that for the VI in the x direction, I'm going to get the d in the x direction divided by the t. So now I can go ahead and plug in. I see that my d in the x direction is 35.0 meters, and the time is 2.12 seconds. So there's my substitution step. Let's now go ahead and solve that and figure out what is that velocity in the x direction with the proper units and sig figs. Gavin, can you tell me what you get? No, 35.0 divided by 2.12 is not 11.8. There you go. And the units on that, please? Very good. So that velocity in the x direction, which we were looking for, is 16.5 meters per second. Notice now my table is complete. There was nothing left to find. All right. Let's move on to page 16 and try another. Now, in this question, it shows us an apparatus that we can use to illustrate some principles of projectile motion. Let me describe what you have here. We have a steel ball right here being held in place by an electromagnet, which is 78.4 centimeters above this catching mechanism, which is on top of this cart, which they call a trolley. The electromagnet and the catcher are mounted on top of this trolley, which is also a cart, placed on this horizontal frictionless track, which looks like a desktop. The trolley is pushed and released so it moves horizontally with a speed of 2.00 meters per second, which means this whole thing is going to move that way to the left at 2.00 meters per second. It's not going to go to the right because otherwise it's going to go off the track. Going to go to the left. Now, when the trolley passes point A, the electromagnet will release the ball. So when we get to this point and the ball is here, it has a horizontal velocity, but it will then be released from this and will then come down to the ground, making its parabolic shaped trajectory down to the tabletop. So first thing I want to know is how long it takes the ball to fall 78.4 centimeters. Then I want to know what is the horizontal velocity of the ball immediately prior to its release. And if the ball lands in the catcher, how far is the catcher from point A? Point A is this point here. So what I could do is illustrate that that is the range, the dx. That would be my dy, which we know is 78.4 centimeters. And this velocity is the initial velocity in the x direction, which we are told is 2.00 meters per second. All right, so let's go ahead and make our chart with our givens for this entire group question. Here's what I know about the x direction. Here's what I know about the y direction. Janicia, can you tell me what the acceleration of the ball always is in the x direction? Very good. Kiara, what is the acceleration always in the y direction? Good. The next thing that we know in this case is our initial velocity. What is the initial velocity, Miriam, in the x direction? 2.00 meters per second. Very good. Sydney, what is it in the y direction? Yep, 0 meters per second. Next thing is our d value. We do not know the d and the x. In fact, that is what I'm asking you for here in part C. I don't know that value. So that is a question mark. Vincent, what is it in the y direction? Okay, and which way is it going to be displaced? Up or down? Down. Now, this is in centimeters. I don't like to do calculations with centimeters. It needs to be in meters. Now, we've done that conversion several times this year. Gianna, can you tell me what that is in meters? That's right, negative 0.784 meters. And then, of course, I do not know the time. In fact, that is what I'm asking you to find in part A. In part A, it says, how long does it take? That means I'm asking you to find the time. All right, so let's take a look at the two directions of givens here. Ryan, which set of givens should I be using to help me get the time? The y, because that's where I know more. So we're going to use the y set of givens to help us get that time. Jacob, can you tell me what equation I should work with if I have an A, a VI, and a D, but I'm looking for T? That is not what's written on your reference table. D equals VI T. There you go. Plus 1/2 A T squared. Now, Alex, what's going to drop out of this equation since I'm using it in the y direction? Yeah, the VIT is going to drop out because 0 times anything is 0, leaving me with D is 1/2 A T squared. If I now isolate the variable T, Nikolai, what am I going to get? Okay, so do the algebra. You can do it on your paper. I'm just not going to show it. What is that equation solved for T? I think we have 3 other questions in this packet that we've already solved for T on the previous pages that may help you.
Oh, T equals the square root 2D over A.
That is correct. All right, now we can do our substitution with units. So that means the time would be the square root of 2 times negative 0.784 meters over negative 9.81 meter per second squared. Yes. Square root of D over 1/2 A. It's the same thing because dividing by a half is the same as multiplying by 2. Devin, can you tell me what you get for that time with the 3 sig figs that we need? Okay, so what's the digit after that last 9? So what do you have to do? Look at, round up. So it's not 0.399. What is it? Round it up. Well, you tell me. When you have to round up a 9, what does it become? A 10. So everything's got to go up. To what? There you go. 0.400, and the units are seconds. That can now go in our chart, 0.400 seconds in both directions. Now we know everything about the vertical direction. Let's now look at part B. Juan, what am I asking you to find in part B?
Horizontal velocity.
So how would I write that as a variable? Because I don't want to spell out HORIZONTALVELOCITY. What do I want to write instead?
VI. X.
That's right. I want to know what is VI in the X. This is actually really easy. Chaudhry, what is VI in the X?
VI and VX are 2.0.
Meters per second. Yeah, this was in the givens. This was in your givens, so there is nothing to do to solve for that. Let's look at part C. Elisa, what am I asking you to find in part C? Which distance? When I say how far from point A, look at the picture. Here's point A. That's where it's going to land. So what am I looking for? dx. That's right, d in the x direction, which means we cover up the y direction and we only look at the x. Max, what equation can I use in the x direction to help me get that d value? That's right, same one. Khalees, what is going to cancel out in this equation when I use it in the x direction because it's 0? Yeah, because A is 0, so this part of the equation is going to disappear, leaving me with D is VI times T. Now, we're going to do this in the x direction, which means that I need the VI in the x direction, which we know is 2.00 meters per second, and the time we already solved for, 0.400 seconds. So when we solve that, Jackson, what does that mean the D in the x direction is?
0.800.
Correct. 0.800 meters. And I'll put that back in my chart to just show that it is now complete. Okay? Questions on number 5? All right, let's go on to number 6. We have a motorcyclist jumping across a ravine as shown below, and it's landing in the middle of a landing zone over here, which is 23.7 meters below the takeoff point. So this motorcyclist is going to come off that cliff, come down, and land there in the landing zone, forming that parabola. Now it shows that the center of the landing zone is 38.5 meters away from the takeoff. So this value here is the what? Shelley, can you tell me what that 38.5 meters is in the picture? Which distance is it? The x, that's right. That's a horizontal value, so I'm going to label that dx. This value over here, Blake, is the what? That's right. That is the dy. Remember, we always add an arrow showing the horizontal velocity that it's launched with, and we also show a time of t at the point where it hits the landing zone. So my time of t would be right there. So I want to know in part A, it says calculate the time between the takeoff and the landing. And part B, it says what is the minimum speed at takeoff that ensures the motorcyclist lands in the center of the landing zone. And then part C is basically a different question, which we'll look at in a minute. Let's go ahead and make a list, our chart, of what we know about the X and the Y directions for our givens up here. So remember, we always start with the acceleration. Emma, can you tell me what the acceleration always is in the X direction? Good. Flavia, what is it in the Y direction? Good. All right, the next thing we're going to put is our VI. Haley, do I know what my VI in the X direction is? Nope, so that's a question mark, but I should know it in the Y direction. Gavin, what is it in the Y direction for these type of projectiles? Yep, 0 meters per second. It's not moving up or down when it's coming off the cliff. It's only a fraction of a second later that it now starts to move down. The next thing we're going to put is our D values. Ryder, what is my D in the X direction? That's right. And Janicia, what's my displacement in the Y direction? And is it going up or down? So I need to make that negative 23.7 meters. Last column or last row, excuse me, is for the time. And Kiara, do I know the time right now? No. So these are question marks. All right, let's go to part A. What am I asking you to find, Miriam, in part A? So T. Which set of givens, Sydney, would be the best set to use to help us get the time? Yeah, how come? Yeah, we know more. So that's what we're going to use to help us get that. I'm just making a note that I'm going to use the y direction. So let's cover up the x direction. It means we know A, V, I, and D. We're looking for T. Vincent, what equation would work with the A, the VI, the D, and the T that we're looking for? That's right. Now, Ryan, something's got to drop out of this because otherwise it's a quadratic equation for time. What's going to drop out in the y direction? The VIT, because VI is 0. So I'm left with an equation that looks like D is 1/2 AT squared. You now need to move that around for the variable T. Jacob, what's that equation for the variable T going to look like?
E equals square root of 2D over N.
Okay, good. Let's go ahead and plug in using the variables from the y column of our chart. So that is 2 times negative 23.7 meters all over negative 9.81 meter per second squared. Alex, can you tell me what that gives us for the time?
2.20 seconds.
Correct. Very good. I'm now going to take that time and come back, put that in my chart. It's 2.00 seconds for it to get to the landing zone over here. Okay, let's go to part B. Nikolai, what am I asking you to find in part B? The VI in which direction? So is that X or Y? That's the horizontal direction. That's in the X direction. Okay, I need an equation, Devin, that I can use to get that VI in the X direction. Isn't that what I wrote down? 2.20? Oh, thank you. I just copied it incorrectly. 2.20. Thank you. Okay, so what equation, Devin, can I use to get that VI if I have an A, a D, and a T? That's right. Juan, what's going to cancel out because I'm using this in the X direction? 1/2 AT squared. That's right, because the A is 0. So that's going to disappear. So this means D is VI times T. Now you have to isolate the VI. Chaudhry, what does that mean the equation for VI is going to become?
We actually did VI.
Yep.
So it's going to be distance times. Wait, distance multiplication of.
What over on this side, it's being multiplied. So to get the time to the other side, we don't multiply. We
Divide.
so D
So
over T. That's right. Now we're going to do this in the X direction, which means I need the X distance and the X velocity. So that means I'm going to take 38.5 meters and divide by 2.20 seconds to get that initial velocity in the X direction. Lisa, can you tell me what that means the X velocity is? Incorrect sig figs. You have 3 in the top, 3 in the bottom. Nope, not 18.0. 38.5 divided by 2.20 is not 18. There you go. 17.5 meters per second would be the correct answer for part B. Let me go ahead and put that back up in my chart. All right, let's now talk about part C. On another attempt, the motorcyclist is taking off at a speed of 30.0 meters per second. They are not taking off at 17.5 meters per second. They're taking off at 30.0 meters per second. I want to know how far from the center of the landing zone the cyclist lands. So let's make a new picture down here. Here is that cliff. Here is the motorcyclist coming off the cliff. Now that X velocity is 30.0 meters per second, which means this motorcyclist is going to go down and out and land way over here. Let's say the landing zone is right there. We know that distance there is 38.5 meters. The distance to fall remains 23.7 meters. This is not changing. We are not changing the height of the cliff. All we're doing is changing that speed. Is the time to get to the ground going to be any different? No, it's not, because look at how we found the time. We found the time using the vertical direction. That involved the height of the cliff. Am I changing the height of the cliff? Which means the time to land remains 2.20 seconds. I'm asking you in this problem, I'm going to call that X. I want to know, what is that X? I'm going to tell you right now, you can't find it in one step. What you can find is the range. You can find the range. And then once you have the range, how would you get the X? Subtract the 38.5 meters from it. Okay, so what I'm asking you to find now, let's just say that I want you to get the dx first, which means you're going to use the X values. I'm not going to recreate the chart. Just know that that VI is not 17.5. It's 30.00. So if I have an A, a VI, and a T, and I'm looking for D, Maxwell, can you tell me what equation I would use? That's right. And in the X direction, remember the acceleration is 0, so that goes away, which means that the horizontal distance we're looking for is that initial velocity going out times the time. The initial velocity coming out, we were told, is 30.0 meters per second. The time it spends in the air is 2.20 seconds, which means that the motorcyclist is going to land how far from the base of the cliff? Please, can you tell me what that total range is? That's right. So we just found that to be 66.0 meters. Now, remember what we said. You want to come up with that X distance because there's your landing zone. So what am I going to do? 66.0 meters minus 38.5 meters. Jackson, can you tell me what that means that distance is? That's correct. Okay. Questions? All right, let's turn to the next page and see how far we can get with number 7. We have a golfer practicing her drive, standing on the edge of a cliff as shown below. It hits a golf ball horizontally. So I'm just going to add my VIX arrow there. She's launching it off the cliff into the sea, which happens to be 37 meters below that. So that is my D in the Y direction on the picture. And we can see after one particular swing, it lands out here. Let's make that 80 point meters. That would be the horizontal displacement. I want to know in part A how long after it's struck it hits the water. Then I want to know the horizontal velocity of the ball. And finally, I want to know the vertical velocity of the ball just before it goes in the water. Something a little different. Let's make our chart. What do we know about the X and the Y directions? Whoops. Shelly, can you tell me what we know the acceleration is in the X direction? Good. Blake, what is it in the Y? Good. Let's now come to the VI row. Do I know VI in the X direction, Emma? Nope, that's a question mark. Flavia, what is it in the Y direction? Nope, that is not a velocity. There you go, 0 meters per second. Now we can come to our D values. Haley, what is D in the X direction? Yep, 80 point meters. We're going to add that decimal point there so we can have 2 sig figs. What is it in the Y direction, Gavin? Almost. It needs to be a displacement. Negative. It's going to go down 37 meters. And then I'm going to put the time. Ryder, do I know the time? No. So these are question marks. All right. Part A, Janicia, what am I asking you to find? Yep, T. Any ideas which set of givens I'm going to use, the X or the Y? Yep, because we know more. Kiara, what equation can we use in the Y direction to help us get that time? Yep. And in the Y direction, the VI is 0, so that's going to drop out, leaving us with D is 1/2 AT squared. So if I solve that for the time, Miriam, what equation am I going to end up with? Miriam, what equation am I going to end up with for T?
T equals 2D over A squared.
So the square root of 2D over A. Let's now do our substitution with units. That is the square root of 2 times negative 37 meters over negative 9.81 meter per second squared. Hold on, let's get that time before you leave. Sydney, can you tell me what that time is? Vincent, can you tell me? Hold on, sit down. I haven't dismissed you yet. Vincent, can you tell me what that time is, please? I'll write you a pass. Sit down.
2.7
2.7 seconds is correct. If you do need a pass to your next class, just stop in and I'll write it for you. Remember, the next 2 pages are homework for tomorrow. Have a great day.